So the first thing we're going to talk about is the atomic laws. We'll talk about who proposed those and came up with them in a few minutes. That's the law of conservation of mass, where mass, guys, is neither created nor destroyed during ordinary chemical or physical reactions. So that's also, you might have heard, conservation of matter. Same thing, all right? Shouldn't be anything, hopefully, super brand new, but we got to kind of just establish that right away when you're looking at a reaction. It can still come in handy later on when we do, we start balancing reactions and we do stoichiometry. The second one is law of definite proportions, where a chemical compound contains the same elements in exactly the same proportions by mass, regardless of the size of the sample. So we've already alluded to this early on in our last unit, saying that, hey, when you have a chemical compound, it's that set ratio. The atoms the atoms of elements are bonded together chemically, which means they're not easily separated. It's going to be that same ratio every single time. So for example, if you have a grain of sodium chloride versus a mound of sodium chloride, it's that same percent by mass that it's listed there. Water, same thing. Whether you have a drop of water or even an ocean full of water, it's the same proportion by mass. Kind of first started with this guy called Democritus way, way back, guys, and he did nothing, really. He just proposed that, matter is made up of these things called atomos, which just means indivisible. So you had these very small things at the bottom. Okay, you don't need to worry about him. He's not in your note packet. Just kind of throwing it out there. All right. He had no supporting evidence. Kind of a creepy looking dude, if you ask me. All right. He's got a weird smile. But anyway, so he's kind of the first one that thought of, hey, what's everything made of? Okay. Kind of getting it down to a smaller level than, kind of what we could see. Fast forward almost 2,000 years, John Dalton came around. Look at what his profession was. School teacher. So you never know. You might see me someday, making the next big thing. Yeah, that's not going to happen with me. Guys, Dalton is the one. He proposed the two laws that you just wrote down. Law of conservation of mass and law of definite proportions. He's the one who turned Democritus' idea into a theory because he could sort of back it up. All right. He said that the atom was, number one, the basic building block of matter. 2, it cannot be broken down chemically. And 3, it's a single unit of an element. So he's known as the founder. He had 4 postulates. You guys need to familiarize yourselves with those postulates. Okay? His theory or model was like the spherical or cannonball theory, where it was a sphere, it had a uniform density, meaning it was always the same, and it could not be broken down any further than that. Big things to remember with Dalton. He was the founder of these 4 postulates. Make sure you are familiar with them. Okay? All matter is composed of indivisible particles, meaning they could not be broken down any further. All atoms of a given element are identical in mass and properties. Compounds formed by combination of 2 or more atoms. Again, definite proportion. And then they can't be created or destroyed. Conservation of matter. Okay? So very basic, but he would again put these ideas, or took this idea and put it into a postulate or a theory. Fast forward almost 100 years, so we can see that, it's 2,000 years before some work really happened. Now it's less than 100. J.J. Thompson comes along. He uses a cathode ray tube. And I'm going to show you guys a video of that in just a second. He proved, using the cathode ray, by using a negative electrode, that the ray was deflected. And it went toward the positive electrode. Okay? So he was the one who discovered the electron. Small, negatively charged particles. Okay? I'm going to show you again a video in just a minute as to what it is. He came up with the plum pudding model. Positive pudding, where you had these bits of negative pieces throughout it. So have you guys ever heard of plum pudding? Some like English dessert, I think. It's not even actually pudding. It's like a cake. Why do they call it pudding? I don't know. The way I think about it, right, also, you know tapioca pudding? Yeah. You got the bits of rice. Anybody like tapioca pudding?
Yes.
Really? Yeah. I don't like it, but more power to you. Is it like hard rice in there, or is it like cooked rice that's in there?
It's chewy.
It's chewy? Okay. I don't know.
How do you know you don't like it if you never
I tried it. I didn't say I never tried it, but no, it's been a long time. I don't know if I have to try it again. But it's kind of like that idea, guys, where you've got this pudding, okay, that's the positive piece, then you've got those bits of tapioca, okay, that are like the negative electrodes. That was his model. So we can see that, hey, Now there are some other pieces in there. It's not just a sphere or a cannonball like Dalton said. There's other pieces to it. It's not that simple. Okay, so it's starting to go further and further. Thompson, like I said, was the first one to figure out that there's a subatomic particle. Okay, so there's something smaller than just the sphere. Okay, a little bit later, Rutherford comes along. All right, he conducted the gold foil experiment where he bombarded a thin piece of gold with a positive stream of alpha particles. We'll talk about alpha particles later on. Basically, guys, it's a helium nucleus. Okay, that's what it looks like. It's just a helium nucleus. So he expected all the particles to kind of go straight through if it's a sphere. But what he noticed is that most of them passed through, but some were actually deflected. And that's what this diagram up here is showing in your notes, is that most of them passed straight through, but a few were deflected off to the sides. Some bounced back. Okay, so that led to the newest model, the latest one, that's called the nuclear theory or nuclear model, where the atom is mostly empty space, where you have a dense positive core in the nucleus. Okay, so he was the one who first came up with the nucleus. Yeah, okay, so now we've gone from a giant sphere that's indestructible to, oh, there's negative particles in there, so there are some smaller parts to it. Now, it's mostly empty space with some negatives around it, floating, and you've got a small, dense nucleus that's positive. How he knew it was positive was because these alpha particles that he was shooting, he knew that those were positive. So if they deflected, again, like charges do what? Opposites will attract, likes will deflect or push away, okay? So I'm going to keep saying that over and over to drive that home in your mind, so you got to remember that. So he, though, provided no information about the electrons other than they were located outside the nucleus. Okay, so he knew that, hey, there's this nucleus there that's positive, and then those electrons that Thompson figured out are still there. We haven't figured out anything with that yet. We good? Can I go on? A couple years later, Niels Bohr comes along. This is the Bohr or planetary model. Maybe you guys made one of these back in like elementary school. Maybe, maybe not, I'm not sure. Okay. He discovered the electrons travel around the nucleus in well-defined paths called orbits, kind of like planets in the solar system. Electrons in different orbits possess different amounts of energy, and then they absorb or gain a certain amount of energy, which causes the electrons to jump to a higher energy level, or what's called an excited state. When excited, electrons will emit or lose a certain amount of energy, which causes the electrons to fall back to the lower energy or the ground state. We're going to specifically talk about those toward the end of this, toward the beginning of next week. So keep that in mind. We'll come back to it and kind of explain it in more depth. We're going to do a lab where you guys are actually going to see this. This is exactly how fireworks work. All right, so we'll talk more about it specifically as we continue along. But after hydrogen, he found out that it didn't work. So it's not the best model. We use it to kind of give us a visualization. You know, take something that's three-dimensional and very complex that we can't see with our naked eye, and we kind of shrink it down and we put it in this very simple model. But like I said, what he found and discovered is that the electrons didn't behave that way once you introduce a second electron. Hydrogen's got one, it worked perfectly, but once you get that second one in there, some other things start to happen. All right, so scientists continue to move along with it. So guys like Chadwick and Schrodinger. Okay, we good? Can I go on? Okay, so they continue to do it. It's still going on today. Where now we have what's called the wave mechanical or cloud model of the atom, where electrons have distinct amounts of energies, and they move in areas, again, called orbitals, very similar to what Bohr said, but a little bit more leeway with it. We don't know exactly where it is, but an orbital, guys, is an area of high probability. All right, high probability for finding where an electron would be. So it's not defined in a ring like Bohr's model was, where you had a specific orbit. It's just an area that's high probability where it is, kind of a circular path. It's developed after the discovery that energy can behave as both waves and particles. And many scientists, and the technique they use is called X-ray diffraction. So as technology progresses, we gain a deeper understanding of what's going on within the atom. All right? Have you guys ever heard of CERN, or a Large Hadron Collider? Okay. There's a lot of these colliders out there. The most famous one is CERN, which is in France and Switzerland, kind of on the border of the two countries. They have worked on it for, I think it's been like 2 decades, and it's up and running and stuff now. Basically what they do is they shoot particles out, and I mean it's miles around in circumference, and they shoot it with increasing energy just to try to collide atoms together, and they have detectors all around it to just try to get any information. You've heard of like the Higgs boson particle? The God particle? No? Well, they're trying to do more research. It's still going today. It's based on Schrodinger's wave equation. Maybe you guys have heard of Schrodinger's cat. That's what this is. Nobody's ever heard of Schrodinger's cat? Oh my goodness. Well, we're going to have to do some... Nobody watches Big Bang Theory? What? No, it's either, is the cat in the box dead or alive, but you can't tell? Oh boy. Oh, wow. Okay, well, we'll just move on from there. So guys, that's a brief history. Know the big ideas, know the scientists, know their discoveries, know what the models look like. Okay? The big thing you got to remember today, you have a picture on your notes of what the wave mechanical model looks like. It's kind of fuzzy lines. Again, probabilities as to where those electrons are. Our next unit, when we start talking more about the periodic table, we're going to talk about electron configurations and do more work with that. All right? But before we get there, we're going to skip that practice for now. You guys will have a chance to come back and do that. Let's start talking about some vocab related to the periodic table and these atoms that we're going to start analyzing. Okay? So take a look at your periodic table in your reference packet. All right, flip to it. You guys are going to tell me what's going on in these boxes. So if you take a look on, it's not a specific table, it's just the periodic table. It gives you a key. So you guys should never have questions as to what this is or what it isn't. Top left corner, you'll find a number with a lot of decimals. What is that number? Yeah, it's the atomic mass. And there's your definition for it, guys, up on the screen. Atomic mass, it's the average mass of all the isotopes, which we'll talk about in a few minutes. What about that bottom left corner? There's kind of 2 numbers down there. Let's go with that big bold one first. Yeah, that's your atomic number. This is going to be a very important number for us, guys, because it tells us the number of protons of the atom. This never changes. It's very important, guys, as we continue and we move on and we start talking about isotopes and ions and things like that. It's very important that you recognize that the atomic number never changes. Other numbers that we're going to look at will change, but the atomic number stays the same because it's unique. It tells you the amount of protons. Excuse me. What about that number that looks kind of like a code right below it? Yeah, that's our electron configuration. We will talk more about what the electron configuration is, guys, in our next unit. So don't worry so much about that one right now. It's the number of electrons in each energy level. Add the numbers to get the total number of electrons. Again, we will talk more specifically about it in our next unit. If we're going to continue going counterclockwise, the big letter in the middle, what's that? Yeah, that's your atomic symbol. All right, that should be nothing new. You don't necessarily have to write that definition down, guys. You should know what the element symbol is or atomic symbol mean the same thing. And then there's the upper right corner. It's got all these negative and positive numbers. And notice, if you take a look at your periodic table, each element has different ones. We will talk specifically about these throughout the year. We have units dedicated to them. These are called oxidation numbers, which they show the possible charges of an atom, or an atom of an element can have. We have a specific unit later on, toward the end of the school year, called redox, oxidation reduction. This is where we will start talking about those charges. For now, it's going to be pretty simple. Okay, we're going to keep things simple for you. So just note that they are oxidation numbers. You'll also see that term nucleons. Nucleons sounds like what? Nucleus. Guys, nucleons are just the things found in the nucleus. There's two particles that are found in the nucleus, protons and neutrons. Okay? Covering the basics of what you guys are going to see, and now we're going to start getting into how to analyze those pieces and be able to count them. You're going to find that this is not super difficult. It's going to seem a lot easier than those conversions that we were doing. And metric system, which is good. Okay? They should be gimme points when you get to tests, especially your regents at the end of the year. Anybody still jotting things down? I know that you guys have seen or heard of all of these particles beforehand, so I want you guys to kind of tell me, proton, what's the charge on a proton? Just positive, negative, or neutral? What? It's going to be positive. Okay? +1 is what it's going to be. Now, each element, we're going to kind of fill it in. You're going to see similarities and differences with those. We start with proton because it's the most important, or one of the most important. Its relative mass, guys, is 1 AMU. Part of your vocab is defining what AMU stands for. Where are protons located? Inside the nucleus. There's two symbols for protons. After you write this down, I want you guys to flip in your reference packet to Table O. Okay, so once you get that down, flip to Table O. If you forget the symbol for a proton, guys, we will be using it all throughout the year. Okay? It's on Table O. It shows both of those. How we calculate it? Simple. The atomic number tells us what it is. So guys, protons, when we start counting protons, neutrons, and electrons, we start counting atoms, protons should be the place you start every time because they don't change. It's the atomic number. Piece of cake, you're going to go right to your reference table for them. Neutron, what's the charge on a neutron? Neutral, right? Probably heard the joke, two guys walk into a restaurant, or a neutron walks into a restaurant and says, how much do I owe you? For you, no charge. Get it? Neutron's relative mass, guys, is the same as a proton. So they're very, very similar. Where are they located? Neutrons are neutral, and they are located in the nucleus. You hear that repetition? Their symbol looks like this. If you look again on Table O, neutron symbol is there as well. Now, these ones are going to be a little bit more challenging to calculate, which is one thing we're going to be practicing. You take the mass number minus the atomic number. Think about it, guys. What this is saying is that the mass of an atom is made up of protons and neutrons. So if we want to figure out the number of neutrons, all we really have to do is to take the total mass minus the number of protons equals your neutrons. Okay? You'll see me abbreviate these. Proton is a plus, P plus, neutron, N0 because it's neutral. Electron, E negative. You'll see me abbreviate them that way. What's the charge on an electron? What's the only one that's left? Yeah, -1. Now, its mass, guys, is 1 over 1863 I can't speak. 1 over 1836 AMU. For our purposes, guys, it's going to be 0. It's negligible. It does not add anything to the mass of an atom. Okay, it's negligible. So its relative mass for us is going to be 0. Where's the location of an electron? Nucleus is getting pretty full. Is it going to be in the nucleus? Yeah, it's outside the nucleus. It's called the electron cloud. There's its symbol. Now, if you'll notice, this is actually in Table O as well, but you have to look under beta particle. Okay? When we talk about nuclear chemistry later on, that's what a beta particle is, guys. It's just an electron. Now, in a neutral atom, and that's where we're going to start, guys, here in a minute, is with neutral atoms. The number of protons equals the number of electrons if it's neutral. Okay? Think about what that means. It's saying that your negative numbers and your positive numbers are going to balance out. Therefore, it's neutral, getting a charge of 0. We'll have a special case where it's not always neutral, but if you have a neutral atom, protons and electrons are equal, and that should make sense. All your positives are going to be balanced out by negatives and vice versa. Okay? On your quiz on Friday, this is what you're going to have to do, is figure out or determine the subatomic particles, protons, neutrons, and electrons. So this is going to help you. Protons, we just talked about that. Where do we get our number of protons from? Atomic number. Okay? Now, you could say it's the sum of the protons and neutrons, guys, but neutrons have no charge, so really, we're crossing that out. Okay? The number of protons, you know what? Don't even write this down. I don't like it. I'm changing my mind. It's too confusing. Number of protons is the atomic number. Okay? Keep it simple. Neutrons, we said, mass number minus the atomic number, or same thing as mass number minus protons. Okay? Electrons, same as the number of protons in a neutral atom. We'll see the special case beginning of next period. An atomic number, guys, we know is you just look at the periodic table, and it's the same as those protons. Mass number, number of protons plus the number of neutrons, and then the nuclear charge is just the number of protons. Because again, nucleus, protons and neutrons are in there. Neutrons have no charge. Therefore, the charge that's in the nucleus is just the number of protons. What I mean by neutral atom, you guys probably know it by now. It's an atom that has the same number of protons and electrons. Okay? So when we talk about neutral, we talk about a charge, we're looking at protons and electrons exclusively. So an example that I have looks like this. Where you would see a charge is in the upper right corner. Now these are two different symbols that we can write. This right here is called symbol notation. Where it shows the symbol and there's other pieces with it, which we'll get into here in a couple minutes. They're both called symbol notation, actually. Two different ways you can write it. There's also called this other one called hyphen notation, where if we were going to write that first carbon in hyphen notation, we would write it like this. Right? They mean the same thing. They show us the same thing. What we're looking for in here is this number. Okay? Now, we know what the number 6 tells us, right? If we look on our periodic table, the lower left corner tells us what number? atomic number. Now, there's two that could be down there, absolutely. The dashes of relational configuration, but this is just telling us our atomic number, so that shouldn't be a problem for us. The upper left number, guys, now if you look on your periodic table, what does it tell you it is? The atomic mass. Now, what do you notice that's different about the number here versus the number that's on your periodic table? This is a whole number. In your reference table, it's a decimal. We're going to talk about why that is in a few minutes. But guys, it's telling us mass, okay? It's telling us the mass, which in a couple minutes when we do some practice, it's going to make a lot more sense, okay? So that's a neutral atom. What we're looking at to determine if it's neutral is we're looking at the upper right corner. Is there a charge located there? If there is, we have what's called an ion. And there are two types of ions that we're going to talk about throughout the year. The first one is called an anion. That is the negative ion. And this is what it's going to look like. Okay. How we see an anion is we take a look again in the upper right corner. Upper right corner of our symbol, this has got a -1. Therefore, we know that that has a negative charge because we've gained one or more electrons. Again, electrons outweigh or outnumber the number of protons. So it's going to be overall negative. So remember, neutral atom, there's nothing up there in the upper right corner. It's assumed to be 0 if there's nothing up there. If we have an ion, there will be a charge. -1, it's called an anion. If it's positive, it's called a cation. Cations have lost one or more electrons. Therefore, the protons, the positive protons, outnumber the negative electrons, so you have a positive ion. Again, same spot. Upper right corners, we're going to see it. So it can either be no charge, meaning it's 0, it's neutral. It could be negative, or it could be positive, depending on how many electrons they have. Now, the easy way to remember, guys, cations, right in the middle of it, you've got a plus sign, that letter T. Okay? It's the way that I remember it even to this day. There's a plus sign in the middle of the word cation. Anion has got an extra N in there, that big N for negative. Okay? So, we're going to practice counting atoms now.